All right. So thanks all for coming. Our first spring SBAR. Yeah. And especially thanks, Steffi. I mean, wow, it's 12, like just midnight, exactly at midnight from Europe. That's the power of Zoom, right? I mean, that's thank you so much. And so just let me do some brief introduction. So Steffi was born in Kerala, India, and grew up all over the country. And Steffi did her undergrad at BITS, Pilani in India, where she obtained a bachelor's in electronics and instrumentation and an integrated master's in physics. And that was also when she started doing high energy experiment. And she enjoyed how it allows her to work on both physics and electronics. And she joined Rogers in 2016 and have been based at CERN since summer 2018. Wow, it's like two and a half years. Right? And in terms of hobbies, she likes quizzes and puzzles, plus anything that gets her outdoors, such as hiking and climbing. Okay, so yeah, let's maybe unmute ourselves and let's give yourself and Steffi a big round of applause. Okay.
Yay.
For everyone else.
Take it away, Steffi, take it away.
All right, so let me share my screen. This one, I believe. Okay, do you see my screen?
Perfect.
Okay, so give me a second. All right. Okay, so my SBAR talk is going to be about detecting particles with CMS. CMS is the Compact Muon Solenoid, which is a large detector at CERN. And this is a photo of it that I took late last year in answer to Stephen's question about going into CERN recently. You can kind of get a sense of scale here with this ladder that's off on the side. So it's pretty large and very beautiful and really cool. And we'll find out more about all of that soon. So the outline for the talk today is basically this. So I'll start by just, saying some stuff about particle physics at colliders, and then describing the Large Hadron Collider and the CMS detector, which is a detector at the LHC. And then we'll talk a little bit about some useful bits of info that will help us understand CMS better. And then we'll just look at the different subcomponents of CMS and how they all tie together to let particle physicists do physics, basically, and try to find new physics right now. Okay, so here's an XKCD comic, which is pretty funny and surprisingly accurate. Well, perhaps not surprisingly because it's XKCD, but it's a great comic anyway. So colliders are basically a really useful way to study particle physics. Starting in the 60s or so, a lot of colliders have been built, and a lot of particle physics discoveries have been at these colliders, including basically most of the particles of the standard model. The difference between colliders and fixed target experiments is that with a collider, you have two beams and you point them at each other, and the beams, the particles in those beams collide with each other. And this is good because it basically makes more energy accessible to the collision itself. There are different types of colliders. There can be linear colliders and circular colliders and lepton and hadron colliders, and they each have their advantages and disadvantages. But for discovering new physics, a hadron collider is really pretty much one of the best ways to go. And the LHC is a hadron collider, as it says in the name, and it's also the circular hadron collider. So yeah, most recently at the LHC, the Higgs boson was discovered. This was in 2012, and it was discovered by two experiments, CMS and ATLAS, one of which is the one that we will be discussing today. The these plots are just from the Higgs boson discovery in the Higgs to gamma channel. So when the Higgs decays to 2 photons. And you can see this little bump at 125 GeV in both CMS data and ATLAS data. And these were basically plots from the papers that CMS and ATLAS put out, basically saying that the Higgs had been discovered. Okay, so the Large Hadron Collider is, like we just said, a huge ring at CERN. CERN is in Geneva, in Switzerland. The Large Hadron Collider actually is in 2 countries because Geneva is on the Swiss-French border, which you can see in this dotted line here. And part of the ring is in Switzerland and part of it's in France. CMS, our experiment, is actually in a tiny little village called Cessy in France, which is out here. There are also a few other detectors, a few other experiments on the LHC ring. There are basically 4 big ones, which are these 4, CMS, ATLAS, ELISE, and LHC-B. CMS and ATLAS are the 2 general purpose detectors, which were made primarily to find the Higgs and then to look for new physics, basically. This is a pretty picture because you can also see Lake Geneva and the Mont Blanc in the background, and it's just nice to give you an idea of.
Where are you now? Where are you? Left-hand side? Oh, you're there. Okay, you're there.
I am, let's see. So that's, no, that's on private sun, that's ATLAS. I'm almost exactly there, yeah.
So you say tomorrow you go to CMS. So, I mean, how?
Yeah, so tomorrow I go there.
How long it takes to go there?
It's about a half an hour drive.
I see.
It's a lot longer by public transport because it's a tiny village in the middle of nowhere. But luckily, especially in these difficult times, we have, things organized with people to be able to get there easily.
Is it difficult that you have to cross the border, or do you have to cross the border? Or are you in France right now?
To cross the border, you do need special forms and things like this right now because of COVID. But you can download this form from the CERN website that says you have work to do and you need to cross the border, and that's okay. So you as of right now, you need to download this form, and if you're traveling between 6 p.m. and 6 a.m., then you need to fill this other thing saying that you're on official work. But yeah, it's a lot better than it was, almost about a year ago. Well, whatever, 9 months ago, when there was literally no traveling anywhere. So, so yeah. So like I said, CMS is our experiment, and this is what it looks like. It's basically a cylinder that's constructed around the beam. So you see this beam line here going through. And we'll talk more about all of what goes in there. So a couple more facts and figures about the LHC. It's 27 kilometers in circumference, so pretty long. And it's underground. So it's about 100 meters underground, although it's different at different points. So because the land itself is uneven. So the ring is more or less flat, but the land is slopey. So at some points it's about 175 meters or so underground, and at some points about 100. And it collides protons every 25 nanoseconds. So that's a lot of collisions at a center of mass energy of 13 TeV. In the beginning, for the first few years of operation, the center of mass energy was lesser. It was 7 TeV, 8 TeV, but now it's 13. And we'll talk more about TeV or tera electron volts as a measure of energy, because that's usually what we use in particle physics anyway. Yeah, this figure just shows that, but in the form of a circle. ATLAS, which is out here, is where the main CERN campus is. We're at the diametrically opposite end of the ring from ATLAS, which is also what you see here. And then in these, some of these other segments are where there are more beam things going on, basically. So the beam dump is here, which is when you want to turn, when you want to stop taking data, you need to get rid of these protons that are in the ring. And you do that by basically dumping them into like a large mass of material, and that happens here. This is a place that should also be cool to visit, but is mostly off limits. So at some point, perhaps one can visit it. And here is the RF cavity. So that's where the particles basically get to get to the really high energy. So the way that the LHC works is that there are a few smaller rings that are connected to each other, which are basically old CERN experiments. So you start with a bottle of hydrogen, get rid of the electrons. So then you have a bottle of protons, and you launch the protons into the first tiny ring, and then those keep getting accelerated and launched into the bigger ring. And then those finally get launched into the LHC. And then there are these RF cavities here, which basically act like kickers. So every time a proton goes through, they get a kick of energy, and then they go through again, and then they get another kick. And then this goes on for a while. It's called a beam ramp up. And then you get two beams, each at 6.5 TeV, which is half 13. And so when they collide with each other, they have a center of mass of 13 TeV. Okay. So the Compact Muon Solenoid, which is our pretty awesome detector. It's really heavy. It weighs 14,000 tons. You might think it's not so compact when you see the person and the size of the detector, but it's mainly called compact because it's smaller than Atlas, which is the other general purpose detector. Although it's a lot more dense, as you can imagine with the 14,000 tons. Most of that weight basically goes into these return yokes, these things that are marked in red here. So 12,500 tons of the 14,000 is just in those. We'll get to what those do exactly, but basically there's a magnetic field, and those just exist for the magnetic field to be able to go through. But again, we'll talk about that a little bit more later. These are some facts and figures, but we don't really need to go into them super in detail yet. What we're going to do is basically see what each of these individual things are, and then we can maybe come back and look at some of these, and they'll be more interesting at that point. For now, I guess the important thing is just to note that the way this works is that the two beams come in through this side and the other side, and the collision happens right in the center there. So yeah, CMS is a really big collaboration, as is the tendency in high energy experiment collaborations. There's over 4,000 physicists and engineers and students and professors from 206 institutes, I think, which are all over the world. Rutgers is one of them, for example, which is why all of us here that are high energy physics people are on CMS.
Can I ask a question?
Yeah.
So how do you be on the co-author list?
So you need to basically finish a few tasks. So the basic idea is, I guess, that you work on the detector in exchange for getting the data. So, you know, your contribution to the detector is doing work, which is either hardware work, which, for example, is one of the things that I'm doing right now, or software work, or maintenance of, you know, all of the different things that need maintenance on the detector. And in exchange for that, you get data, and you get to analyze data and do physics, basically, and also be on the author list.
Got it.
So, and yeah, like all of the CMS papers have everyone that's an author. So there's typically like several thousand authors on every paper. And there's also a lot of papers, as you can see. There's over 1,000 papers in the past 10 years. So a lot of physics keeps coming out of these experiments. Although what everyone's really looking forward to is the next discovery, because most of those results are importantly ruling out various theories. But it would be nice also to find new and unexpected things at some point. Yep. One common description of CMS is a cylindrical onion because it has all these layers that are built around the beam pipe. And yeah, what we're going to find out over the course of this talk is how this works. Right, so some useful bits of information. The first thing that you need to know to understand all of the stuff about how CMS works is the particles in the standard model. So the standard model is this extremely successful theory which describes the strong, weak, and electromagnetic forces. It's very consistent and a good description. It has some gaps, which are things that don't really come out of the standard model as it is right now. And a lot of the work in particle physics is basically trying to find answers to those questions. But the particles that are known in the standard model right now are all in this little cartoon here. So there are all of these particles, and also there are antiparticles. So there are quarks, and there are 3 generations of quarks. The up-down, charm-strange, top-bottom, formerly known as truth and beauty, which were more poetic, I guess, but yeah. So these are quarks, and then you have also 6 leptons in 3 generations again, which are the electron and its neutrino, the muon and its neutrino, the tau and its neutrino. And then you have the gauge bosons, which mediate different forces. So you have the gluon for the strong force, the photon for electromagnetic, and the W and Z for the weak force. The strong force being basically what keeps, for example, neutrons and protons together. The electromagnetic force being, I guess, the most familiar in that it's the one that you study in physics and so on. And then you have also the weak force, which is which you can see in some reactions, like in nuclear reactions and such. And then there's the Higgs boson, which gives mass to things, which is also within the standard model. So let's see. Yeah, one thing about the quarks is that you can't find a quark in isolation. So quarks need to come together to form either mesons or baryons. If you have an even number of quarks, you get a meson. And if you have an odd number, then you get a baryon. In the detector, so the way it works is when you have a particle collision and you get a quark out of it, it immediately hadronizes. Hadronizes being forming hadrons. And how it does this is it basically pulls a quark anti-quark pair out of the vacuum. And this process basically goes on with all of the free quarks till you get a bunch of stable particles. No, till you get a bunch of mesons and baryons, which aren't necessarily stable, but then they decay into other things. And in the end, what you see, so you never actually see one of these quarks by themselves. You always see a particle at best, even if it's a very unstable one. And so this collection of particles is called a jet in particle physics. Yep. Anything else? Okay. So
can I ask a stupid question?
Yeah, no, go for it. No stupid question.
So you say, so if quarks are never free, so how do we know there are 6 quarks?
Through a bunch of experiments, basically. That question makes a lot of sense. So the first postulation for the existence of quarks was, I think, from a deep inelastic scattering measurement, where, well, first it was from the theory, but then it didn't seem like there was a way to prove it because of exactly this reason. You can't find them by themselves. But then there were these deep inelastic scattering measurements that kind of showed if I remember right, that there was some sort of substructure within neutrons. And it kind of said that there had to be like, 3 things within, which were like 3 quarks.
I see. So basically not like a direct evidence, right? I mean, like real, just observe 1 quark is not possible, right? That's what
No. Well, no. But there's lots of theory stuff that basically, it's very well validated in that, for example, like after the up, down, and strange were discovered, for example, the existence of the charm quark was postulated before it was actually discovered because it fell out of the theory. And then it did exist indeed. So a lot of the behavior for these things was in manners that were expected. So, it follows, I guess, the thing that any scientific theory should, in that it made predictions that you could prove. So,
Fair enough. Thanks.
I think it's a fantastic question. If I can chime in, you need quantum chromodynamics to tell you about the quarks, because as Steffi said, the only thing we have access to are the hadrons. So like basically what she said, but yeah, you need quantum field theory to tell you that there are these quarks and those properties and such.
Got it. Thanks.
Yeah. Oh yeah. Feel free to, tell me to go slower, stop and ask questions. All of these things are highly encouraged and they make talks more fun anyway. Okay, right. So like we said, quarks in general hadronize to form jets. So this isn't true for the top quark, which is a lot heavier than the other quarks. As you can see, it has 173 GeV, whereas the next one is like the bottom at 4 GeV. So the top quark basically almost instantaneously decays. So it's the only one that doesn't hadronize. You never find, you basically almost never find a hadron that has a top quark in it. Instead, it decays directly to a W and a B. So the way you know that there was a top quark there was if you see a W and a B together. And yeah, this is also true of several of the other particles in here. So all of these decay. The top quark we just talked about, the Higgs boson also decays, and as do the W and Z, all fairly quickly. And also the tau lepton. So for all of these, you don't actually see these particles by themselves in the detector. What you see instead are decay products, and you reconstruct the fact that those things existed at some point. And then finally, you have the neutrinos, which are almost completely non-interacting. And so they just escape the detector. So yeah, if you take away the ones that decay, what you get are these particles left over. And indeed, these are the things that you see in your collider. So you see electrons, muons, photons, or rather, I guess, you need to build a collider in a manner such that you can see electrons, muons, photons, and jets. And you can use the fact that you can see all of these other things to work backwards and calculate how many neutrinos should have been there, basically using conservation of energy. And so with all of these, you kind of get a complete picture of what happened at any collision.
Steffi?
Yeah.
Rena asked a question. So she asked how, in the chat, how does the Higgs boson give mass to things?
Right. This is a question that I can't answer on any really deep level because it's not something I have a great understanding of at a deep level. But the general idea is that the Higgs field that different particles interact at different strengths with the Higgs field, and that determines how much strength, how much mass they get. Yeah. Okay. Going on. Okay. The next thing that is kind of important is the passage of particles through matter. So particles do different things when they go through different types of material. And you basically use a lot of these properties to be able to build detectors that can then detect those particles. So with electrons, what usually happens is a decelerating electron gives out some radiation. This radiation is known as Bremsstrahlung radiation, and it's in the form of photons, basically. So then what happens when an electron hits a bunch of matter is it starts to give out these photons, and then photons tend to pair produce. So they give you an electron and a positron. And then this kind of continues outward. So from the electron and the positron, the electron again goes and gives a photon, which does that. And the same with the positron. It also gives another photon, which gives out, another pair, and so on and so forth. So you get a shower, basically. And all of your energy is contained within that shower. So in the end, you have particles that don't have enough energy to continue decaying anymore. And then if you can add up all of the energy that had been deposited throughout the shower, then you basically get a measure of the initial energy of that first electron, or the first photon, as the case may be. For hadrons, it's somewhat similar. You basically put material that has a high Z in front of your hadrons, and then there are a lot of nuclear interactions that the hadrons have, which also result in showers like this. And you do the same thing again, where you add up all the energy from the showers and you get a measurement of the energy of the hadron. And I guess the last thing that's kind of useful is just talking a bit about some of the conventions. So mass, momentum, and energy are measured in units of electron volts. The fact that they're all always measured in electron volts also kind of makes it easier to be able to compare things and get an idea of what's a big number and what's a small number. So that makes it useful. So the mass of an electron is 0.5 MeV. The mass of a proton and a neutron are about the same, a little bit less than 1 GeV. And then the mass of these bosons, for example, the WZ and the Higgs are 80, 91, and 125 GeV approximately each. And the center of mass energy of collisions is 13 TeV. So as you can imagine, there is a lot of energy that's available to create particles, especially if their masses are of the order of hundreds of GeV. So this is why it's kind of nice to go to higher and higher energies, because you start to be able to access spaces for particles with higher and higher masses, for example. So one of the reasons that the Higgs boson was discovered at the LHC is because it was the highest energy collider to have been built up till this point. Also, I guess that the answer there is not as simple as that, because there were also design optimizations made in order to be able to find the Higgs boson at the LHC. But yeah, basically, higher energy allows you to see more stuff and have more interesting collisions. And then there's detector coordinates. So it's a right-handed frame, and the Z direction is basically along the beam axis. The X points towards the center of the LHC, Y points up, and the origin is at the collision point, so also the center of the detector. And then phi is the angle that whatever you're measuring, so let's say momentum, phi is the angle that the momentum makes with the x-axis. And theta is normally the angle that momentum makes, for example, with the z-axis. In particle physics, we don't use, in high energy particle physics, you don't really use theta that much. Instead, you use eta, which is a function of theta, and basically translates like so. And the reason that you do this is basically because of some functions that eta has. Differences in eta, I believe, are Lorentz invariant. So it works out better when you're doing calculations in the space. And then the other thing is that you don't use raw momentum. You use PT more often, which is transverse momentum, or the momentum that is perpendicular to the beam. And the reason that you do this is because what you're doing when you're colliding two protons is essentially you're colliding two partons within those protons. So you're colliding two of the quarks, and then you're getting stuff out of it. But you don't know how much energy of that 13 TeV is in each one of those two quarks. That can be anything from 0 to 13 with different probabilities. So what you do know, however, is that there's energy going in this direction, but there's no energy at the beginning perpendicular to the plane. So if you calculate the transverse variables so the transverse momentum, for example, for all of the particles, then you know that you can conserve momentum in that plane, and you should get a 0 if you add everything up. And so this is a good way to measure missing ET. So you add everything up, and then you have some excess. So you say that there should have been an energy in the opposite direction, and that's being carried away by neutrinos. This is basically how you get a measure for neutrinos in your events. It's also how you, there are searches also that look for missing ET that are looking for new physics. So there's the idea that if there is new physics that's not interacting or very weakly interacting with the standard model, then it would escape your detector and also register as an energy, a missing energy signal. So that's another way that you can look for new physics. Okay.
Can I ask a question?
Yep, sure.
So how do we know that there's no like particle with energy bigger than like 13 TeV?
Simply because there isn't the energy to create it. So when you're starting off, you just have these two protons with, up to 13 TeV. But if you had a particle with more energy than that, it would need to get that energy from somewhere. So, since, again,
maybe
it's basically...
there's an unknown particle. With beyond standard model that energy is bigger than that. I don't know.
You mean, okay, yes, that is indeed very possible. And
okay, that's possible. Okay.
Yep, absolutely. Yeah, you're right.
13 TeV is like technical limitation.
Yeah, the LHC was designed to operate at a maximum of 14 TeV, I believe.
Got it.
So the idea is to one day build an even bigger collider that would reach 100 GeV and be really huge. And it would be expensive, however, and therefore the funding and such are questions. But yeah, the hope is to be able to probe those spaces with, higher energy reach.
Beyond standard model, basically. Yeah.
Yep.
Got it.
Yeah. Okay. Okay. So now with all of that out of the way, we can start talking about CMS a little bit more in depth. So the first thing that we talk about is the magnet. And there were these cool illustrations that were online with different parts of the detector highlighted, which I kind of like. So the magnet is this segment in here. And there are portions of the detector. In fact, almost all of these components are inside the magnet, except for the muon system, which is outside. And we'll find out why soon. So the solenoid, the magnet is the solenoid in CMS. And it basically, a solenoid gives you this kind of an electric field. So it's a nearly constant electric field on the inside of the solenoid, which is super nice because when you have that kind of a setup, you have this, high school, college physics type situation where you have a constant field and you have a particle going through that field and the particle curves. And a measure of its curvature basically gives you its momentum. So CMS has a really good magnet. It has a magnet that generates a 3.8 Tesla field, which I think is, I think Atlas is 2 Tesla, but I don't really know this for sure. Anyway, so it has this really strong field, which is nearly constant, which is super nice because it gives you really nice bending for all of your charged particles. And we'll see how the tracker uses those in a moment. So it's made of this superconductor called, niobium titanium. And it's pretty large. It weighs a lot. So it's 12.5 meters, 6 meters in diameter. That's that measurement there. And weighs 12.5K tons. So this magnet was in a lot of ways what determined a lot of the design aspects of CMS, because it's a size such that the ECal and the HCal, so the other components that you see in here, needed to be able to fit inside this. So you wanted to get the biggest solenoid that you could get that would allow you to fit an ECal and an HCal inside. But also the bigger that it gets, the more expensive that it gets. But my advisor likes to tell this fun story about how the price wasn't actually necessarily the complete limiting factor of how big the magnet was and therefore how big CMS is. But instead, it's the fact that this magnet needed to be transported from wherever it was made to this little site in Cessy, in this tiny village in France. And so the determining factor in the end was some sort of transportation thing about how big it could possibly be and still fit on the roads or clear the clearances and like fit on the trucks or something like this. So yeah, that's a pretty cool story. It was completely assembled on the surface. In fact, a lot of CMS, all of CMS was completely assembled on the surface. And then there was this huge hole in the ground and like the parts were lowered into 100 meters underground one by one. So that was true also of the magnet. And then this is a picture from 2008, 9, somewhere around there, I guess, where the magnet was being inserted into this frame that had the muon detectors and the return yoke. So the return yoke, which we were talking about a little bit before, is these red segments here. It's made of iron, and it's basically what a return path for the field. So it's like where it goes through when it goes back there. What that means is that in the rest of this part of the detector, the field is in the opposite direction. So with muons, you have them go one way inside and then turn around and go the other way outside because the direction of the field changes. For everything else, they stop within the detector in this volume, so you don't really see the change. But this is an additional way to calculate momentum for muons because you get like one measurement inside and then another measurement out there. Okay.
Can I ask a question?
Mm-hmm.
What's the typical temperature, like, say, in the measurement or in the room?
So there's a separate cooling for the magnet itself, And that is a few Kelvin. It's
Yeah,
really cool.
yeah, I'm thinking like, so this niobium titanate should be like, you should use liquid helium to cool down. So I'm like thinking like how it affect the measurement, the temperature of it, how would that affect the measurement? But maybe they consider that. I mean, yeah.
I don't know the details very well, but I do know that the cooling is a big part of the effort that goes into the magnet. Like there's this huge cooling system, and there's like all these rooms with liquid nitrogen and liquid helium. I think it gets cooled in several steps. So I don't remember the order. I think you'd probably know this. I think it's nitrogen and then helium. So nitrogen to get it down to a certain temperature, and then liquid helium to get it down to a lower temperature. And also another segment of the detector called the tracker also needs to be really cold. So both of these segments get a lot of this cooling thing. And yeah, it's completely essential to the operation that they be maintained at that temperature. So it's, if the cooling stops to work, that's a full-on crisis that needs to be rectified before you can go any further.
Got it. Thanks.
Yeah, sure. Okay.
Hey, Steffi, do you know why they need the return yoke? Like, what if you didn't have a return yoke? I didn't know that it was where the magnetic field lines come back, but now I'm thinking, well, why do you need to put something there?
I guess I would imagine it's so that you contain it in a small region, so that you don't have like, presumably if you didn't have the return yoke there, it would just like go in through the, like whatever ion substances were in
Nearby.
the vicinity or something like this. Yeah.
Okay, so you'd have like fields running around
Right.
in the cavity, and you don't want that,
Yeah.
I guess.
Yeah, absolutely. In fact, even with the situation as it is, there are like these alerts and such for the magnetic field being on, because like if you go near the detector when everything's turned off, but it hasn't been too long, so when it's still ramping down and stuff, apparently you still find like if you have something iron on your arm or something, like your arm gets lifted up and such. So
Really? Okay.
yeah. And if you have any implements that use iron, then you aren't supposed to be anywhere near there, etc., etc. So
Cool.
probably it's a safety measure. I guess it also helps the muons for sure. I mean, no, actually for sure it also helps the muons, because you understand better the field, and therefore
That makes sense. That's
what
right.
you expect to see there.
Good point. Thanks.
Yep. Okay. All right, and then now that we have the magnet out of the way, we'll basically go from the in out. So the innermost thing is the tracker. So the beam pipe is made of beryllium. This I found out recently and I thought was really cool. So the beam pipe is super expensive and it's made of beryllium. And the reason for this is because that has a really low Z. And therefore, you're trying to minimize the interactions as much as possible before you, for stuff going out. So it has a really low Z, very minimal interactions, and then you see most of the stuff as it goes out. The tracker, yeah. So the this is the collision point, and then the tracker starts like right there. So a few centimeters off of the collision, you already have the pixel layer beginning, and then beyond that you have the strips. So these are extremely finely segmented. So the pixel in this tiny volume, well, symmetric about phi, and also on the bottom. So yeah, symmetric about phi. But the pixel has 124 million channels. And so the way that these work essentially is that you have a resolution. So you have pixels, and then these light up when a charged particle goes through them. And the information that you get is an electronics readout of which panels lit up. And then what you try to do is fit these to a track and reconstruct as many tracks as you can. And this tells you what particles you expect to see with what momentum. So yeah, you have the pixel with 124 million channels, and then outside of that, you have the strips, which are a lot coarser, but still very fine. And these have 9.6 million channels in totality. And the tracker is really, CMS's tracker is very good. And this is in part because you need to be able to distinguish primary and secondary vertices. So the primary vertex is where the collision happens, so right there. Usually it's a bit offset. It's not exactly at 0, it's a little bit offset, and that offset is important. So you want to be able to calculate it from interpolating your tracks backwards. But you also want to be able to see secondary vertices. So for example, with B quarks, what happens with them is that you usually do this thing called B tagging for a jet, where you identify that it has a B in it. And this is useful for a bunch of different physics searches. And how you do that is you see that the B is a bit displaced from the primary vertex, and then it forms its own secondary vertex. So you want to be able to reconstruct the tracks of that jet backwards and see that like the vertex that it forms is a little bit away from the first one. So it has an impact parameter. And yeah, you can do that with the tracker. The tracker is all silicon, which is also very good because it's quite radiation hard. In the 10-ish years of operation, it's still performing basically as well as it did before, which is not quite true of most of the other subsystems. And it's right next to the beam, so it's really impressive that it works so well and still works so well. The way that these work, which is something we'll see similar concepts also in some of the other detectors, is that you have essentially a piece of silicon and there's an electric field in it. So when a charged particle goes through, it ionizes the material. And so you get electrons and holes. And then since there's a field, the electrons go towards the positive side and the holes go towards the negative side. And then based on how many holes or how many electrons, so in this case, the readouts on the hole side. So based on how much charge you get, you make a determination of the fact that an energy went through. Here, actually, for the silicon trackers, you don't care about how much energy is deposited so much as you just want it to clear a threshold. So as long as this is minimum ionizing, it should basically give you enough of a readout for the channel to light up and you to basically see that something went through there. Yep, so that's how that works.
Steffi, I got a question for you.
Mm-hmm.
If you've got like millions of channels, how the hell do you instrument this electronically for data acquisition? How is that accomplished?
Yeah, that's a whole discussion on itself, especially for the tracker. There's a lot of cables. So for the tracker, each of these segments is built into like what's called a petal that's about that big. And then you have a bunch of wires that run through each of the segments within the petal. And yeah, and then you basically make sure that your wires are separate and read them out. Yeah. But it's, the large number of channels in all of this is why, for example, not even just necessarily the pixels, is why when you basically look at the CMS detector, you know what you see is a bunch of wires running all over the place. So yeah.
So are the signals, do they go to like a ASICS module or something like that? Is that how you handle
Well, yeah.
That
So
many channels?
yes, absolutely. So for each of the subsystems, there is a set of front-end electronics. So starting with like the pixel and strips, for example, there are some electronics that are right next to the readout itself. And so there's some amount of processing that goes on right there. And then you repackage your data and you send it to an FPGA for processing usually. And that is located also underground, but a little bit further away from the detector. So most of those are accessible even while collisions are going on. And then you do further processing there and then send it up to the surface and then distribute it, and you can make measurements and so on. Yep.
Cool. Yeah, that sounds complicated, but really neat. Thanks.
Yep. Okay. Next, there's the electromagnetic calorimeter, which is also known as the ECAL. As you can see, it's right outside the tracker. So with the ECAL is CMS's other great triumph because it's a homogeneous calorimeter. So calorimeters are basically detector components that measure energy. And for what happens here is, like we discussed before, you want all of your electrons and photons to basically create showers and deposit all of their energy. And for the ECAL, it's really nice because you basically have a huge block of material where all of the energy gets deposited and then read out simultaneously. So it's a really expensive solution because you need these crystals. So these PbWo4 crystals is what's used for the ECAL. But it's also really efficient. So it gives very high resolution data for the measurements of energy for the electrons and photons, basically. Yep. For the NCAP, so almost all of the detectors also have these two differences in that there are detector subcomponents for the barrel and for the NCAP. So the barrel's a barrel, as you can imagine, and the NCAP is what covers the two sides of the cylinder. So it's the same also for the ECAL. So most of the interesting physics that you get is at low etas usually. So almost transfers to the beam axis. And what you get as you get higher in eta or closer to the forward direction is a lot more interaction. So you get a lot more data basically from all of those. And therefore, those parts need to be more radiation hard in general because otherwise they decay too fast. And also, you need to be more careful about how you're employing your readout usually in these places, because it's usually harder to pick anything sensible out because there's so much noise in these parts. So for example, the ECAL NCAP has this thing called a pre-shower, which it has to try to reject some of the pi zeros. So pi zeros are these mesons that get produced a lot. And in jets, for example, and they decay to 2 photons. So if you get a lot of pi zeros and photons from pi zeros, that could mess with your calculation of photons that you expect to be actually from the event. And so what happens with the pre-shower is that there's this section of lead, and then there are some silicon strips beyond that. So the lead causes the pi zeros to shower, and then you get a measure of that in the silicon. And only after that does it go to the NCAP. The ECAL and also the HCAL work with scintillators, essentially, which are, so this PbWo4 is a scintillator, which is basically a material that gives you a photon or a certain number of photons when a charged particle goes through them. Usually the amount of light that you get is quite small, and not always the wavelength of light that you're going to be able to see with photo detecting electronics. So what you almost always have with a scintillator setup is you have an attached wavelength shifting fiber, which collects this light and changes it to a frequency that is easier for your electronics to read. And then it goes through a PMT of some kind, so a photomultiplier of some kind, which takes that signal and amplifies it a lot. So in general, with a lot of these detectors, the signals that you get are going to be very small. So you always need to find some way or the other to be able to amplify them if you want to make a good reading. And yeah, I guess that's everything here. Okay.
Can I ask something?
Yep, sure.
So about this rejection of the pi zeros, so they shower and become photons, right?
Yes.
Yes. So you reject them because the photons become too soft, or how do you then distinguish them from like the event photons?
Yeah, because you see the in the silicon, you can kind of see that there are two branches of photons that came from right before it. So you're like, okay, that was probably a pi zero because it looks like a pi zero decaying into two photons.
Ah, I see. Okay, thanks.
Yeah. Okay, and then there's the HKL, which is very close to our hearts, some of our hearts, because it's the subdetector that my advisor works on, and therefore the subdetector that Brandon and I work on. And the one that I've been, doing hard physical labor for the past couple of years, basically, which is lots of fun. Anyway, so the HCal is the hadronic calorimeter, which works in a similar manner to the ECal in that what you have is a scintillator, and you get scintillation light from charged particles passing through it. Okay, so it's slightly different from the ECal in that here what you have is a brass and plastic scintillator sandwich. So it's not a homogeneous calorimeter like the ECal is, but it's instead what is known as a sampling calorimeter. So you have like this bit of brass, and then your hadrons go through them and have a lot of interactions and shower. And then you calculate, after this, you have a plastic scintillator. So whatever makes it out of this brass layer, you measure the energy. And then if it pushes all the way through onto the next brass layer, it showers some more. And then there's another layer of scintillator after that. So you have a few of these layers, and you kind of measure the energy as it spreads out. This comes with its problems. Basically, the main one being that you're going to be losing some energy in the absorbing brass layers, but you basically just try to calibrate and fix it like that. Yeah, the HCal has been upgraded over the past couple of years to have finer segmentation and to use silicon photomultipliers instead of the old kinds of photomultipliers that they were using. And yeah, this is part of what I was doing, which was really fun because it meant being able to hang out in the detector and be upside down, for example, and try to fix things. So it was really fun. And also now we're working on the laser system, which is basically used for calibration and to measure the amount of radiation damage that the HCal is seeing over the course of collisions.
Hey, Steffi, can you talk about the new photomultipliers a little bit more?
Okay, so they're basically these tiny chips, and they're silicon based. So they have several advantages over the others. One, that they're radiation hard again, so that helps, especially with the high Lumi LHC and such. It helps a lot to have something that'll be able to resist that large amount of particle flux, basically. And they take a lot less power than the old kinds of photo multipliers used. So the old ones were like order of hundreds of volts, and these are just like order of 1, so like 5, 7, so on volts. So and they're a lot smaller, which means also that you can have a lot more electronics fit in the same place, which is also what allowed us to do this segmentation in the first place, because you always had the outputs from the detector, but you couldn't connect them to enough photomultipliers to be able to read them out separately. So in the beginning, you were just reading the whole thing out together. But now, since you're able to process them separately, you can, get how much energy is in each of these segments. And by doing that, you get more information, which you're then able to use to do better data analysis.
Okay, thanks. Is this the same technology that eCal uses for photomultipliers?
No, so eCal was doing their own upgrades. I'm not sure what the status is now, but at least at the beginning, they didn't have silicon photomultipliers either. I think primarily because they were super expensive up until a few years ago. So, they only became a technology that is being used a lot somewhat recently. And I know that there is an eCal upgrade happening, but since I don't know what it is exactly, I'm not sure if silicon photomultipliers is what they're shifting to.
Okay, and you call them SIPMs, the new ones, is that right?
Yep.
Okay, and the old ones are PMTs?
They are, so there were different ones for HB, HE. HB and HE had the same ones, which were HPDs, hybrid photodiodes. And then there was something different for HE and HF, which I don't remember anymore.
Gotcha. Thanks. Thanks a lot.
Sorry, HF and HO, yeah. HO is not getting upgraded at all, so it'll just have whatever old thing it had. Yeah. Okay, so I see that we're basically running over, but just a couple more slides, so I'll be done.
Steffi, sorry, I got one more question for you.
Yeah, sure, absolutely.
So you talk about doing these upgrades and stuff. I mean, all of this stuff is layered together. How do you get in and fix things or change things? And
yeah, that's a good question, and it's actually a lot easier with CMS than it is with Atlas, and this is in part because of how it was constructed. So it weighs 14,000 tons, we said, but it's also built of 15 different layers because they had to have them in like thin enough layers that you could lower them in through this huge hole in the ground. So now those layers kind of move back and forth. And since each of those weighs 1,000 tons, how they move is also actually really cool because each of them is attached to these hydraulic lift things, which reduce the normal reaction just enough that you can then use like this system of ropes basically to pull them back and forth. So based on what you need to work on, you move a certain number of layers back, have it accessible, go do your stuff, and then like when everything's done, the whole detector is going to be closed up. And yeah.
that is okay, cool. That is surprisingly well thought out.
Yeah, absolutely. It's quite impressive. Okay. So with the muon system is the last one that's outside of everything else, like we said. So in there, you have a really nice field and you calculate all of the stuff for everything except the muons, basically, and the neutrinos, but those you don't calculate ever. So yeah. So the muons kind of work on a similar principle as the tracker, sort of, but only in their operating principle. Otherwise, they're kind of completely different. So these detectors are really large. They're the outermost thing. And as you can imagine, as the detector gets bigger, it gets quite humongous. So you definitely can't afford to have something that's very finely grained, finely segmented, and especially not if it's a lot of silicon, because that would be really expensive. So for all of the muon system, what you have is gas detectors, and it has 3 different types of gas detectors. It has drift tubes and RPCs here. RPCs are resistive plate chambers, and CSCs or cathode strip chambers and RPCs on the end caps. So the barrel where there isn't as much occupancy has the drift tubes, which are kind of not as efficient as the CSCs, but it's good enough for this part. And the reason that you have two of these kinds of detectors for all of this is because you want the drift tubes and the CSCs for the resolution information, and you use the RPCs for their timing information. So one gives you better resolution, the other gives you better timing, and then you combine both of those to get a good readout, basically. All of these work on kind of similar principles in that, so for the drift tubes, for example, for each segment, you have a gas chamber, and then you have a wire that runs through the center of the gas chamber. So it comes out of and into the plane. And then if a charged particle goes through, it ionizes the gas. And then, so this is positively charged. The electrons go towards the positively charged wire. You see where on the wire the electrons hit. And then you measure how much time after the original signal it hit. So from where on the wire it hit, you get a measurement of, along the plane where it was. And then from how much time it took to get to the wire, you get a measurement of how far away it was. So therefore you get a two-dimensional resolution measurement basically on muon position. For the cathode strip chambers, it's a similar operating procedure where you have so you have these blue things here are cathodes, so they're negatively charged. And then you have positively charged wires here. So again, you have a gas. When a charged particle goes through, it ionizes the gas, and the electrons go towards the wires, and the ions go towards the cathode. So the wires are in one direction, that gives you one measurement, and the cathode gives you the other direction of measurement. So again, you get two-dimensional reading there. And finally, you have the RPCs, which again, you have a positive plate, and negative plate, and a gas chamber in the center. And particle goes through, it ionizes. The ions, the electrons again go towards these strips. And this happens really quickly. Again, for all of these, you kind of have a field difference that basically makes your particles go towards, in this case, the wire, in this case, the strips and wires, and here towards these detectors. And you see that there was a charge, and the resolution here basically depends on the resolution of your RPC. So how thin these strips are, and how long they are as well. But it's really quick, so it gives you better timing than the other two. Yep, and that's how you see where your muons are. Again, if you can build muon tracks, then you know the momentum of the muon based on how it's curving. Okay, so that's all of the parts of the detector. The final thing is that—
Hey, Steffi, you have a question in chat.
Sorry, I don't know how, that's how you do it.
Okay.
I see chat now.
Yeah, you can see. Okay, good.
Okay. What you're trying to detect particles in, is it just a beam of light, a beam of protons? So the way it works is that, I'm not sure I understand the question. So the way it works is that you have a beam of protons right at the center. So in here, you have one beam of protons coming in this direction, another beam of protons coming in this direction. The two protons collide with each other, and then a lot of stuff comes out. And the stuff that comes out is basically anything from the standard model. Those things then start to decay into standard model particles. And so basically what you have is collision stuff, and the stuff is what you detect in CMS. So, there's different kinds of particles, and there's so they're everything. There's some electrons in there, and some photons, and some muons, etc. I'm not sure if that answers the question, though. Does it?
Yeah, right now we'll ask if she finds there's any question. Yeah, no worries.
Okay, all right, sure. Okay, so the last thing is the trigger system. And what that is basically a way to limit how much information you're reading out of the detector. So like we said, collisions happen every 25 nanoseconds, sorry, typo there, which gives you a rate of 40 megahertz. That's a lot more data than you can read out. Not only is that a lot more data than you can read out, you also don't want to read all of it out because a lot of it's just boring stuff that doesn't teach you anything new. So this is where the trigger comes in. The trigger basically takes some information from all of the subsystems. So it quickly looks at the ecal and sees how much information's in there, at the hcal, see how much information's in there, etc. And if it looks like an interesting event, which is basically a lot of deposits in the ecal and hcal, then it says that, okay, it fires this thing called a level 1 trigger, which says that, for now, record that data. And further downstream, you analyze it a little bit more, you build some of the tracks, you continue to see if it's interesting. Okay, question, how do you get a beam of protons? The beam of protons is at the beginning what you start with. So in the beginning, you have a bottle of hydrogen and you strip out the electrons from the hydrogen. So what you are left with is protons. And then you launch those protons into the LHC. So you have two separate pipes, one that goes in one direction and the other that goes in the opposite direction. So that's how you get your two beams of protons. And then at each of these detectors, at each of these experiments, you basically make your two beams interact with each other and then you get the collisions and stuff. Again, let me know if that answered it. And if not, we can discuss more. So yeah, here, so the rate decreases from 40 megahertz to 100 kilohertz at the level 1 trigger. And then once you do your further processing and stuff, you can reduce that to 1 kilohertz, and that's good enough for you to be able to read out. Okay, so that's everything. That's all the systems, and let's just see how all of it comes together. So based on everything that we heard about the detector, hopefully this makes sense. So this is an image basically with what kinds of signals different particles would leave. So the muon is a charged particle, so it leaves some tracks in the tracker, but then it doesn't interact in the ecal. So the first layer is the tracker, then the ecal, then the hcal, and then the muon chamber. So it doesn't do anything all this way here, and then it starts to turn the other way and leave deposits in here, the drift tubes. All right, so that's what the muon does. The electron is again a charged particle, so it leaves tracks here, and then it decays completely in the ecal. A charged hadron, again, leaves tracks in the tracker, doesn't do much in the ecal, but goes and decays all of its energy out in the hcal. A neutral hadron can't leave any tracks in the tracker because it doesn't ionize in the silicon there. It doesn't create any electron hole pairs, but it loses all of its energy in the hcal. And finally, a photon doesn't do anything there, but leaves energy here. So as you can see, they all have different signatures, which is basically what you use to kind of work backwards and reconstruct what particles were. This is a simplified view, because right now what is used at CMS is this thing called particle flow, which is a lot more, a fancier way of doing something very similar, basically. But doing it in such a manner that you get an improved resolution than you would by just following these methods. Yep, I think that's, this final thing is just an image of a real event from a long time ago, but in CMS with all of the different tracks and the energy deposits. So the red, I guess, is ecal and the blue is hcal. And you can see some jets. So with different views, you can see, different kinds of things of what's in those particles. Yeah. So yeah, that's a summary.
Steffi,
yeah.
There's a question from Reina.
Sorry, let's see.
So Reina say, yeah, you can just read.
Okay, then how do you get a beam of muons or a beam of Higgs bosons? You don't get a beam of muons or Higgs bosons. At best, you get in one of those collisions. So every 25 nanoseconds, you have one collision. So what comes out of that collision is a probabilistic thing. So, let's say once every 1 million times, you get a Higgs boson out. And that Higgs boson could decay to muons, for example, which would give you some muons. Or you could have, a lot more often, you could have, for example, a Z boson come out, and that Z boson could decay to muons. Or you could just have an interaction that gives you, from the proton collision, something else happens and a muon comes out directly. So what governs what you see coming out of a proton-proton collision is basically all of these quantum field theories. So, it depends on the cross sections of different kinds of reactions. Some things are going to be more probable than others. Some things are going to be very rare. Most of the interesting things are very rare. So basically you want to, try to isolate one of those interesting events. So, and then if you see an interesting event just once, then you don't know if it was a fluctuation of some kind or if your electronics failed or whatever. So then you want to basically collect data for long enough that you get a statistical answer that you're happy with, and then you can claim a new discovery. Let me know if that answers it. Or not. But okay, any other questions? That's basically the end of the talk. So we can, all right.
Yeah, thanks, Steffi. Let's unmute ourselves maybe first, and then let's give another round of applause for Steffi and all of you. Here, right. Thank you.
Thanks, Steffi.
Thanks.
Way to go.